the whiteboard, yes or no? So we studied today the last part. The last part is two fantastic theorems can help me to compute line integral and surface integral in one super easy way. The first one is called Stup Theorem. Okay, Stup Theorem. Okay, Stup Theorem I say, okay, you have, for example, you have a surface. Suppose that we have S. Be a piecewise smooth. Remember, smooth indicate differentiate. Orientable, you know, okay, we have two faces. Therefore, we can define two normal vectors in and out in R3. With boundary, C is a curve, okay, C equal del S, so boundary S surface, in the positive direction, similar to the idea for the green theorem, is quantum co-y, but it's okay. I want to explain in detail this part. Positive direction. Okay, and also we have a vector field. The famous vector field PQR. And PQR as a function that depending of x, y, and z, but they are continuous. So not only PQR are continuous, PQR are continuous, and its derivative is also continuous. So is one fantastic way to indicate this is that these PQR functions belong to the C1. C1 means continuous. This capital C indicates continuous. They are continuous, and also 1 indicates is partial derivative is also continuous. So we can write in English, you know, PQR are continuous and is their partial derivative also continuous, but the mathematical language look like that. Continuous in S, that's the surface. And see this situation, number 1 and number 2 happen, then we have a fantastic formula case. The line integral in the closed curve of the vector field that dr circulation, pero es mandatory que in this theorem the curve is closed, is equal the surface integral of the curve of the vector field that ds. O sea, this is similar pero multidimensional for the green theorem. Green theorem state relationship between one line integral and one double integral. So this is more general. This is in R3. Okay, green is in R2. But this is more general. Is in the 3D. So it's a curve of this. Okay. Let me explain the convention to understand this. So we have a surface. Suppose we have a curve. Look, in this case here. Suppose we have a curve in 3D. In counterclockwise orientation. And suppose we have a surface. Like that. Okay, this is S and this is C. Okay, C is equal del S, so the boundary. Now, this formula is okay. So the compatibility, que Stup suppose was compatibility, okay, the 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 comp or compatibly is, suppose if you walk around the boundary, with your head is in the direction okay, you choosing orientation of the surface, que es basically orientation of normal vector, no? Normal vector, comma, your left R is over S. Let me translate this in more understandable language. Suppose que this is you. Okay? And here, or you here, doesn't matter. In any point on the boundary. If you're walking, and I suppose que you choosing the orientation of the surface like that. Look, it's a normal vector. Remember, there are two possibilities, no? Out or in. But I suppose this. So you're walking around the boundary, your head point to the normal vector direction. Now you left R, this right, left point on the S. So this is your left R. Look. Okay, left, no? Left. And this is also left. So the direction is this. See, this is completely opposite. It's not important. Because the only difference is that these have a minus sign. Because it's not totally compatible with the idea. Okay, similar, a little bit more complicated to the green theorem. However, well, the green theorem has no specification exactly what surface. So any surface is possible. So for example, we have a family of surface. Suppose we have again the same sketch. The boundary. And we have surface, is something like that. Okay. Y I assume the same idea. I assume that the normal vector is in the same direction because I want. Remember, I assume this. In this case, maybe in this direction, it's exactly the same direction of this. Therefore, the orientation using this rule is exactly the same, doesn't change. Okay, it's the same because I'm walking like that. This is me. My head point to the normal vector and my left R point on the surface, over the surface. So it doesn't matter. So we have family. You can see it's weird because we have a family of the surface that satisfies this idea. There's no specification one arbitrary. So we have, for example, exactly the same boundary, but I assume that my surface is like that. It's a flat. And the green theorem, Stup theorem is valid for the same. This is the normal vector. This is the orientation. That is positive orientation. It's the same, exactly the same. So there are no specification what surface we are using. Therefore, this phenomenon or this idea is called surface independent independent of a curved surface integral. Okay, so now suppose that at the beginning of the problem we have one surface, but you can change the surface if you want. And what is the reason? Okay, you can, well, because I want to select one easier surface. Not necessarily the surface is given, so another surface. I bring one example, only one example, guys. Today we studied the two theorem. Stup is the first one, and the second is divergence theorem. We study at least one problem because it's too long. Now, immediately I want to start review for this. Okay. Example, unique example for the Stup. Well, no, in the review packet we have more examples of this. Suppose that we have vector field example. Suppose that we have vector field. Is minus y, comma x, 0. Okay, and the surface is x squared plus y squared plus c squared equal 4. And c is greater than or equal to 0. This is my surface. It's defined by this equation under this restriction. And to say what kind of surface it is, guys? Same question anytime. What kind? Sphere. Very well. A sphere with the radius is, Gerardo? What is the radius? 2. Entonces, actually, ¿es sphere o hemisphere? Hemisphere. Because this restriction say that you care only the top part. Entonces, the sphere, okay, actually the sphere is this. Hemisphere. And this is the surface that I want to call S1. But we have another surface que es X2. X2. Okay, let me see in the. Well, okay. X1. X1, no, X. That is the reason, no reason. X1. This is my. And the orientation in this moment is, so you assume that the orientation of the surface look like that. Well, this or this is out. It's out. Entonces, the trajectory, you walking in the curve in that direction. In that direction. That direction. Remember, this is me. My head point to the normal vector. I can move a little bit if you want, so not necessarily. For example, in this case, the head is point to this normal vector. In this case, point to this. So you can change a little bit the angle. Okay, you walking around the curve. Now my left arm is over the surface. Okay, so this is compatible, no problem. I try to apply Stup Theorem. So I want to verification. So I want to compute, first of all, the line integral, and secondly, no, first of all, the Stup have right hand side, left hand side, no? Right hand side, left hand side. In the left hand side, we have a line integral. In the right hand side, we have surface integral of the curve. Let's do it first, right hand side. Okay, because the goal for this example is verifications too. No, in one specific example. No? Okay, entonces the right hand side gets the surface integral. You compute the curve of the vector field is. Guys, do be familiar with this notation. Oh, this notation. This is del cross F. It's the same, no? Okay. AYK. Partial derivative with respect to x. Partial derivative with respect to y. Partial derivative with respect to c of PQR. Que PQR in our example is minus y, x, and 0. Okay, when you compute that, you know very well how. The answer is 0, 0, 2. Wow, nice. Okay, now one possibility to find the surface integral of this vector field case is super easy because it's constant. Is compute the normal vector. The normal vector I did before in the last class for the sphere is x over 2, y over 2, c over 2. It's totally radial. Es xyz divided by the radio que es 2. Entonces, when you perform the dot product curve f, dot product normal vector. This is one way to do that. Not always like that. Another possibility is parametrization. Another possibility is, xyz. Pero let's do it that way. I don't know. In my paper, I do it that way. Dot product x over 2, y over 2, c over 2. Es obvio que the answer is c. It's a scalar function. Entonces, the only thing we need is to set up. So basically, we have in this moment the surface integral of the curve f that ds, bueno, no ds, sino es m, that m, ds. So far is, bueno, is this, que sí, I did that part. But I don't know ds because I need to do something. Entonces, in my opinion, the best way to do ds is using spherical parametrization. No? In spherical parametrization, so in one corner here I write spherical parametrization because it's a sphere or hemisphere, whatever, is 2 sine phi cosine theta. It's the formulas to state relationship between x, y, and z in spherical coordinate. 2 sine phi sine theta, and c is 2. Actually, the formula is r or rho, pero rho in this case is 2 because it's sphere, it's constant, cosine phi. And phi vary in this case from 0 to pi over 2 because the hemisphere. Remember, phi is the angle. Suppose that you are doing the view in 2D. This is c, this is x, something like that. Remember, phi is measured from c equals 0, from the axis c, sorry, to this. Okay, this is c0, phi 0, sorry, and phi equal pi over 2. Si es complete sphere, no, entonces pi. Pero en this case, no, es hemisphere. And theta, it's completely theta, go from 0 to pi. And this is our domain. Our domain look like that. So you want to do graphics. No, not necessarily do this. But I like to illustrate, no? At least for educational purposes. No? This is 0 to pi. And this is 0 to pi over 2. It's a rectangle. This is the advantage to doing spherical. Because we are doing XY, entonces no spherical, no rectangle, entonces it's more complicated than here. Okay, entonces now I need to find the vector value function. The vector value function is the parameter is phi and theta. And you rewrite this I want to skip this part because it's too long. So now, if you differentiate with respect to phi, and you differentiate with respect to theta, and you have performed the cross product, it's no surprise. Okay, the answer is 4 sine phi. It's exactly the same for the Jacobian. I promise, guys, que Friday, next Friday, que es the last day, I want to dedicate one lecture. No, it's another topic, a super interesting topic around the multivariable calculus. But it's totally out. It's general knowledge, you know. If you don't like, you have big accent Friday, next Friday. But it's a big picture about integral and everything, this theorem together. And I prepared something about the electromagnetism. Que maybe you need to take in the university, right? Entonces you see que es similar, it's exactly the same idea. It's actual value, sorry. Compute the Jacobian que we studied before. Que Jacobian is when you change a variable, the most typical is polar or cylindrical or spherical. In this case, spherical. No? Or parametrization. Actually, it's the same because we change the variable. Okay? And you say, well, professor, no. Because maybe a 3D or 2D, in this case, combination 3D, 2D. So this thing I try to clarify next Friday. No, this next. Okay, this is expecting because you know very well that in spherical, the Jacobian is rho square sine phi. And who is rho in our problem? It's 2. And 2 square 4. Okay. Okay, so my surface integral look like, okay, this one. It's C. But okay, C, I know. But C expressed in spherical coordinate is 2 cosine phi. Look here. Multiplication by the Jacobian. O Jacobian, no. Es the cross product, ¿no? Que es 10. The 10 is 4. Pero actually it's the Jacobian. It's the fantastic way. D phi. The theta and phi vary from 0 to, so the region is, this is the region. From 0 to pi over 2. And from 0 to pi. Okay. And I did that. It's no big deal. It's super easy. And the answer is, okay, use, for example, let's do it. Bueno, because it's easy. 2 times 4 is 8. And you separate into integral. One integral que is only theta. And another integral que is only phi. Es cosine phi. Sine phi. D phi, no? However, I remember that this is similar to the double angle formula. Double angle formula is sine to phi is equal twice sine phi cosine phi. Well, so we need one extra 2, no? But this is easy because we have 8 here. So one possibility is break it down. This 8 like a 4 and 2. So you put 4, no 8. And these 2 I put here. And this is also the sine phi. 2 phi, double. Entonces the integral this, yeah, the answer is a pi. It's easy. Okay. Antiderivative sine is cosine, but you have another extra 2. Evaluate this part as 2 pi. The final answer is a pi. Okay, I am doing the idea in the right hand side. Okay, right hand side, the Stup Theorem is the surface integral. However, I want to do because the goal of this problem is verification. The left-hand side is the line integral. So I need to do line integral in the close. It's important que it's a close. It's a close, exactly like a green theorem. So Stup is the 3D version of the green. Of the vector field que es F dr. But my curve C, remember, was this. And this trajectory. Okay. Okay. So now it's easy parameterization because actually it's 2D because it's XY plane. Okay. Actually, the parameterization of this curve is x equal to cosine t, y is equal to sine t, and c is 0. And c is 0 is not important to take care because if c is 0, when you compute the dx dy dx dy, it's obvious that this is 0. So this dimension is not important. The derivative cosine is minus sine dt. And the derivative sine is cosine dt. Okay, you put everything together. If you want, you can change a little bit this because my problem is 2D, like a pdx plus q dy, line integral in this way. It's integral from, I forgot to say get t vary from 0 to pi because it's completely circle. 0 to pi, that you change the line integral and one common integral of the calculus 1. And p is, I forgot the vector field. The vector field was, remember, vector field was negative y comma x comma 0. However, you evaluate the vector field in the vector value function. The vector value function, well, in this case, it's a curve, it's not surface, one parameter, t only. So you evaluate the vector field in the R of t, right? Okay, this is equivalent to say, who is y? Negative y. So the vector field is negative y. Who is negative y? Or who is p? This is PQR. Look at that, PQR. Who is p? It's negative y. Who is y? Y is 2 sine t. It's negative 2 sine t. Entonces, parenthesis, no bracket, because I consider it like in this way, either way. Okay, PQR. Sorry, PQR. Let me erase this angular bracket because actually it's no angular bracket, and now it's parenthesis. It's minus 2 sine t. Because in our specific example, p is negative y. Yeah, I know in the parameterization que y, so basically you plugging in the parameterization into the vector field. Okay, because I want only the part of the vector field que es overlap, o sea, coincident with the curve. Multiplication by dx. Who is dx? Bueno, dx es minus sine, entonces minus 2 sine t dt. Okay, dt. If you want to put dt in the last part, but it's okay. Plus p, q. Who's q? Q is x. It's 2 cosine t. And multiplication by dy, que dy is 2 cosine dt. And what about z? C is 0. C is 0 in the curve, and C is 0 in the vector field. R is 0. Basically, our problem is actually not 3-dimensional, it's 2-dimensional. Okay, perfect. And this is super easy. You multiplication of 4, you multiplication of this is 4, and you factor out, well, negative and negative become positive, and sine squared plus sine squared is plus cosine squared of 1. Entonces now f4 multiplication by 2 pi is 8 pi. Wow, and we get exactly the same answer. In this case, look like relatively easy using the line integral. But no. In other problem, no, you see in the review package. So we have two possibilities. Suppose we need to compute the line integral, and you convert to the surface integral using the curve. Oh, this is one option. Okay, maybe it's easier or maybe no, depending on the problem. Okay. Stup is the version for the green in 3D and allow us convert the line integral. The most important requirement is that this line integral is on the closed curve. See, it's open, no, it's closed. Look at in the definition. Look at the formula. Look at the formula, right? Look at the formula. So when some people explain interpretation of this, interpretation is always complicated, no? Okay, but it's okay. Let's move on to the second theorem that we studied today. Second theorem that we studied today is divergence theorem. Okay. Divergence. Sorry. Do you follow me? Do you follow me? The divergence. Okay. The divergence. Divergence theorem. This is fantastic. This is sometimes some people call Gauss theorem. Because they are a strong connection with the physics. Yeah, the Maxwell equation. The last day I want to talk about electromagnetism and Maxwell equation. And the first Maxwell equation is the Gauss. Okay, so they are a strong connection with the divergence theorem. Divergence theorem is, okay, we have some hypotheses. First one, we have surface. B, a closed piecewise smooth. And what is the reason? Okay, always a piecewise. Let me try to explain this idea because you need to understand the hypothesis of the theorem. Smooth means totally differential. But piecewise say that not necessarily whole in the whole domain is totally differential. Suppose that we have something like that. Suppose that we have one cubic, no? It's a differential here. It's a differential here, but in the corner no. But it's piecewise, it's smooth. The differential for different interval. It's the stupid thing to say piecewise smooth. It's differentiable, but in all whole domain. See, it's the differential in the whole domain, no corner, is much better, of course. Surface, comma, which is the boundary. Okay, you say this theorem only talking about something and its boundary. Of T. Who is T? T is a solid. Okay, we have a closed surface enclosed one solid with normal vector pointing outward. This is my first premise. The second is we have vector field. PQR. And this vector field belongs to the continuous one. That means that PQR are continuous and is a partial derivative. It's also continuous. It's important. On the solid T. Okay? Then, the theorem say, then, okay, entonces this theorem connecting. One surface integral. And the closed surface, wow, this is the first time I saw that. Okay, this is line integral and the closed line. It's a line integral. This is surface integral. Okay, but in the closed surface of the vector field, that yes, exactly the same we saw before, but it's connecting by the triple integral. Wow, triple integral and the solid T of the divergence. That is the reason it's called a divergence theorem of the vector field dV. Okay, entonces what is the interpretation? The interpretation is, this is a flux. This is clear que it's a flux. Flux and one specific, look, surface. A surface, closed, of course, surface. And we need to compute the flux. Well, okay. So flux. So flux out. The theorem says, suppose que es out. Si es in, bueno, it's the same formula, but opposite sign. This is a flux. And the sake the flux is equal the triple integral and the solid. This is no vectorial integral. It's a scalar integral because divergence is a operator, no? Que convert vector field to a scalar function. And this is the classical triple integral that you see before. The one scalar function dV, and you apply whatever you want. You apply Cartesian, cylindrical, spherical, okay. But the most important is the interpretation. This guy. Okay, this guy, remember, is divergence, que indicates source or sink. Okay, we have inside here. Suppose that we have different source of electric field or water, out, or we have sink, is a drain in opposite direction. Entonces, when you integration on the volume of the solid T, okay, the solid T is the space inside this. Actually, you are doing the summation, any source inside this, positive or negative. And this give me information on the flux. So make sense. Super intuitive idea to understand the divergence theorem, because the amount of source or the amount of sink we have inside enclosed is the reason that we have flux outside or inside. Bueno, si es outside positive, si es inside negative, no? According to the convention that we are using here, que normal vector, you suppose que is outward. Okay? Entonces, what is important? It's important because suppose que we have a complicated surface, like in this example. In this example, we have a complicated surface. Look. And this complicated surface is formed by a cubic. Let me try to use another color, like that. Chum. A cubic. This is surface. This is my famous surface. It's a closed surface, and the distance is, and this cube is 1. Okay, it's unit cubic. 1. In any edge, the length of it. You have this is S, and you have vector field. The vector field in this example is given, no? 3x, comma, xy, comma, 2xz. You need to compute the flux. And the entire surface is closed of this vector field, ds. This is complicated because we have actually it's a surface closed, but it's formed by different surface. For example, this face I call S1. This face I call X2. This face is called S3. So different faces, right? Okay, this face, look. Actually, we have 6. No? So my problem, let me finish it's a X5, is this. What about 4? 4, wait. 4 is down, is 4. And finally, X6 is the bottom part. So you are doing, by the classical idea, you integrate X1 plus integrate X2 plus until X6. That's a too long problem. No, no good. It's no big deal. It's relatively easy because the normal vector is supposed to be here is I. In this case is J. It's relatively easy, pero it's long, no? However, the efficiency way, so you know the divergence theorem, well, okay, to say you convert this surface integral in this complicated compound surface and one triplet integral and the solid T. Who is the solid T? Is the space inside here. Okay? Surface is totally out part. So the wall, no? However, the space inside is a solid. Of the divergence of this vector field, this vector field. dB. And that's it. End the story. Let's do it. One more time, we practice a little bit. The computation for the divergence is super easy. Core is complicated, divergence is easy because it's partial derivative p with respect to x plus partial derivative q with respect to y plus partial derivative r with respect to z. Entonces we expect, es obvio que we expect a scalar function que you plug in inside the triplet integral. Partial, this is PQR, and the vector field. Okay, partial derivative p with respect to x is 3, just 3. Partial derivative q with respect to y is x. Partial derivative r with respect to z is 2x. Entonces 3 plus 3x. My problem is now compute the triplet integral in the solid T of the function is 3 plus 3x dv. Entonces I have no idea si I using Cartesian, si I using polar, or I using cylindrical, or I using spherical. Es obvio que no. Es obvio que we're using Cartesian x, y, and z because it's a cubic, no? Entonces basically this is my integral function. Chan. Okay, 3 plus 3x. And you integrate, for example, in that order, dx, dy, dz. And x, y, and z vary from 0 to 1. Because this is the cubic, it varies from 0 to 1. Look at that. 0 to 1, 0 to 1, 0 to 1. 0 to 1, 0 to 1, 0 to 1. And this is super easy. Integration that part, evaluating between 0 and 1. After, it's a number. To say see it's a number. Well, let's do it because it's too easy. Look by hand. When you integration with respect to x, because I make decision in this order, this is 3x plus 3x squared over 2, no? Evaluating between 0 and 1. This is 3 plus 3 half, no? and 0 is 0. Entonces, well, this is 6 plus 3 is 9 over 2. This is the answer for the first integral. But the second integral and the third integral, look, is integral 9 over is 9 over 2y. Evaluating between 0 and 1 is 9 over 2 again. And the C happened exactly the same. Entonces the final answer is 9 over 2. I did in that way, guy. This is too long, stupid. I did, but it's too long. No, not important. You get exactly the same. It's beautiful. Diverging. And this is the most important in diverging is, okay, when you using that, when you have a compound surface, formed by different pieces, in this case was 6 pieces, but not necessarily 6. Suppose I define one compound surface que es in 2 pieces. So one sphere and another sphere, different radius, one plane in the middle, I don't know. So you don't care surface by surface separately. No, you are doing the solid and the triple integral is solid. Entonces, what is the integrand function? Oh, the integrand function is divergence. That's it. In the story. Super easy. Super straightforward. Okay. Entonces we dedicate today. The time of today. We have a lot of time. Good. And Monday and Wednesday, we have a lot of time to solving the review package step by step. Super easy. Now, Friday is the day que we present to you some interesting topic, totally out of the course. But I suppose que improve a little bit your general knowledge, no? About multivariable calculus. Okay, let's do in the sample 1. Question 1. Question 1 is line integral x dy is given in that way, no in the classical f dot dr. But it's okay, you know, you are familiar, we have different ways to express it, the line integral, ¿no? En la que escalar, la que vectoria, Entonces, it's giving also the parametrization of the curve. This curve is parametrization using this parametrization in 2D. 2D and 3D. I suppose that this is x, I suppose that this is y. Therefore, you copy x equal to t, you copy y equal 3t, and you differentiate, why not? Dx is 2 dt, because derivative this is 2, and this differential, so it's dt. You ending in dt, and dy is 3 dt. And now substitution. You convert this in one common integral, like a Cal 1. I forgot to say, important thing, I forgot always, I don't know why, it is better from 0 to 1. This is the domain of this. 0 to 1. You copy x. Who is x? 2t. Who is dy? 3dt. Plus. Who is y? 3t. Who is dx? 2t. 2dt, sorry. So actually we have 3 times 2 is 6. 6 plus 6 is 12. 20, no? dt. Now the integration is a piece of k, is 12 t squared over 2. Evaluating between 0 and 1, this is 6. Evaluating between, the answer is 6. End story. Super easy. Line integral. Any question? Any question? No? Clear? Answer me. Clear or you are sleeping? Clear, very clear. All good. Okay. This is question 1. Okay. Question 2 now. Well, question 2 is compute the curve of the one given vector field, verify is conservative or not, and try to find the potential function. See, existing. Question 2 is, this is the vector field, it's given. X squared plus y squared, comma, xy. It's 2D, vector field 2D. This is P, this is Q. Entonces you compute the curve of this vector field. The formula is qx minus py. Remember, the curve in 2D is not vector. It's a scalar function. Because it's one component. It's the k component for the in 3D. Entonces you differentiate. That's it. Partial derivative q with respect to the x is y. Minus partial derivative p with respect to y, it's a constant, is 2y, no? This is minus y. And minus y is not 0. Therefore, non-conservative. Conservative vector field. And what's going on with the potential function? The potential function does not exist because this is a property only for the conservative vector field. Otherwise, no. This is clear or confused? This is a moment. So you have some question. What is the potential? Clear, super clear, super clear, super clear. Okay. Let's move on to number 3. Number 3 is, well, number 3 say, compute the, it's exactly the same, but another vector field. Okay, you have a vector field. The vector field is sine x plus y, comma, sine x plus y. Wow, they are twins function, x plus y. The component is the same. It's a P, it's a Q. Okay, you compute the curve of this vector field. The formula is qx minus py. And you find the partial derivative p q with respect to x. Entonces derivative sine cosine. Es negative cosine, ¿no? Negative, es cosine, ¿no? Cosine. Cosine x plus y, ¿no? And the derivative, the argument is 1. And minus derivative p with respect to y is, bueno, es the same. It's cosine x plus y. And derivative the argument inside the cosine is 1. It's 0. Therefore, yes, it is conservative. Vector field, therefore, the potential function exists. I need to find. Remember the potential function is you find the anti. You take p. What is the formula? You take p and antiderivative. It's anti-gradient. I need to find what gradient. Okay, what function? Sorry. When you compute the gradient, give me the original vector field we have in the board right now. So you compute the anti-gradient. So good power. You take p, because I suppose that this expression comes from of the partial derivative with respect f. F is the potential function that I'm looking for with respect to x, and this is partial derivative f with respect to y. Therefore, in order to find my f, I compute the anti-derivative. So antiderivative, the p with respect to x. So you take antiderivative sine x plus y dx. Bueno, antiderivative sine es cosine, ¿no? Es minus cosine xy. Pero remember, I find the antiderivative with respect to the dx. Therefore, you consider the y as a constant and like a one number. So no important this. I care only the argument. But in this case, the argument is super easy because the coefficient is before the x is 1. To say stay the same. You put plus something. You put plus something if you want, but not important this. It's an arbitrary function that depending only of the another variable que es y. Because the antiderivative that you compute is with respect to x. Entonces now, any function, I don't know, exponential, whatever, power function, is perfectly legal when you differentiate. You know? When you differentiate, you consider, when you differentiate with respect to x, you consider that this guy is constant and disappear. Likewise, antiderivative q with respect to y, that's the formula. Is, in this case, sine x plus y, but in this case, dy. So it's the same. By the same reason, no? Because you differentiate with respect to y now, you consider x constant, antiderivative sine minus cosine, and the argument, well, the argument is just x. So you don't need to, you apply substitution, maybe, no? You suppose u equal x plus y, du equal dx, and to say now, whatever, see, I don't need to explain, this is calculable. Plus another function that I want to call h, que depending only the x, no? And now you compare. So what is the idea? What is the idea? The idea is, in order to find the potential function, you put together any expression. So the potential function x comma y is equal, look, I collect it, I collect this, oh, I collect this, I collect this. And what about this? I suppose that this is 0. Entonces, the potential function in our example is just minus cosine x plus y. End the story. Any doubt, guy? Any question? Do you understand very well the idea behind? I want to explain is. Go ahead. I understand. Okay. Remember, we need to understand right now every detail because this is the review for the test. Okay. Any particular doubt about integration or where come from this guy can disappear? I have no idea where come from. Entonces now, suppose que we are doing Bauer. Suppose que you are doing Bauer. Pero no necessary. Suppose que I try to find the vector field que confront of this potential function. And you differentiate. Derivative cosine is sine x plus y. But you differentiate with respect the x. Like that. Boom. Entonces, when you differentiate derivative cosine minus sine and derivative argument is 1, boom, I got it. And likewise, derivative is the potential function, sorry, with respect to y, derivative is the same. It's obvious it's the same. Okay? Entonces, I write back in opposite direction to the vector field is given at the beginning, is, by the way, is conservative. Any question? Any question number 3? Do you understand very well? Number 4 is similar. Number 4 is compute the curve, but in this case 3D. And number 4. Entonces, 3D is, bueno, a little bit more long. No complicated, but it's long. So, in number 4 question, we have vector field. Vector field is given is y e to the x, comma, e to the x plus 1, comma, e to the c. And remember, we suppose this is PQR. PQR, remember, are real scalar function que depending on x, y, and z. And together in this organization form a vector field. because vector field is the collection of the vector. You associate one point on the R3 with the one vector, no? It's a function, it's a function, it's a function. And PQR is a scalar, no? So what is the formula? What is the formula? What is the formula for the curve? You find the curve. It's the first thing you should do. The problem say compute the curve. Okay, I do what? IJK, but this is like 3D. So we need to do like cross product. This is equivalent to say del cross product F. And who is del? No, del is partial derivative with respect to x. Totally hypothetical, no? Ese like a mnemonic device to remember this thing is very complicated in another way. And you copy here PQR. And PQR is, in our specific example, is y e to the x plus 1, and e to the c. Wow, fantastic. Fantastic. So I recommend doing that way. You copy I here. You copy I here. Open the parentheses. You delete mentally this and this. And you focus on that part. Partial derivative with respect to y of the function e to the c is 0 minus partial derivative with respect to c of this function is also 0. Wow, we have no component in I. 0i. Minus j. Remember, the guy is negative. So you focus in that part. That part. So you differentiate this and this. Partial derivative e to the c with respect to x is 0 again. Bush. 0 again. Minus this and this. Look. This and this. And partial derivative with respect to z is, this expression do not depend on z, is 0 again. Entonces, 0j. And what about k? Okay, is you delete now this column and this row, and you focus in that part. Entonces, in this case, yes. The partial derivative with respect to x is e to the x, minus something, and partial derivative with respect to y, you have here something is 1 to say it's e to x. Wow, e to the x minus e to the x is 0k. The curve is the 0 vector, is the vector 0, 0,0 ijk component. So that is conservative. It is conservative. Conservative vector field. Therefore, we can find the potential function. That the potential function exists, and we need to find. So far, everyone follow me? You are boring to do this cross product using the determinant at the beginning in the first chapter we start. Yes. Victoria said, yes, I'm boring to do this. Okay, so now potential function. The potential function, you find the anti-gradient. So you have 3 components in this case. You compute the component antiderivative p with respect to x. It's antiderivative y e to the x dx. Okay. Entonces now you consider que the only variable is and y is a constant, you put outside. And antiderivative of the exponential is the same. Exponential is the only function that is exactly the same with. Okay, plus something. And this something is a function that I want to call g, depending of the another variable, no x anymore, y and z. Okay, because any function depending of y or z or together or both, when you differentiate, when you go back, you differentiate with respect to x, the derivative is 0. Entonces yo assume this. Okay, guys, this is not mandatory. I put because I am professor, entonces I am a little bit picky. Pero no. You omit that part. You leave it like that. Look, so you leave it like that, it's perfect. And finally, you get the collection without repetition. Without repetition. Okay, now antiderivative q with respect to y. It's antiderivative e to the x plus 1 dy. Bueno, this not depending of y. Therefore, entonces you put outside this. And this is y. Entonces, basically, I copy in elegant way, you know, e to the xy plus y. Plus something. I don't care. Now the last antiderivative r will repeat the c. Well, r is e to the c, no? Let me see. Oh yes, this is r. This is antiderivative e to the c dc. I see. Yes, e to the c. Plus something, no? Plus one arbitrary function. In this case, arbitrary function que depending yc. In this case, arbitrary function que depending of x and c. And this is arbitrary function p que depending of x and y. Okay, now finally, potential function equation. Potential function is a function que depending x, y, and z, of course, in 3D. And you take the collection. You take the collection without repetition. To say, I see, wow, look at that. This is the same. You take only one time. E to the x, y. One more I take. Well, I take y. This y. One more I take. One I take e to the z. And that's it. End the story. This is my potential function. And the potential function, of course, I can use it to compute the circulation or the work done in between 2 points without do anything. The man can evaluate in between the start endpoint minus the start point, if you want. But in this case, no. In this case, the objective of this problem is only compute the potential function. Any question? Any question? No? No. Okay, let's move on to the number 5. Number 5 is more complicated because, in this, in calculus, normally happen the complication of the thing increasing exponential, no? We start easy, no too easy, not too hard, a little bit hard, hard, super hard, so increasing too fast. Okay, but in this case, number 5 is no big deal. Number 5, no big deal. Number 5, let me copy the evaluate. You need to evaluate this integral. Entonces es from 0, 0, 0, 1 point in 3D, and 1, 1, 1, que is another point in 3D. Entonces this is a little bit weird because it's the x plus y plus c, parentheses, dx, dy, plus dy, plus dc. Sometimes happen. Just give me the problem in that way. This is completely. I try to illustrate because they are different way, different book, different option. Normally you see in that way f that r, no? In the way we always study, no? And you see that this PQR, f PQR, and dr by definition is dx, dy, dz. Pero es dot product here, pan. Entonces, in this case, using my imagination, I suppose que f vector is repetition this 3 times. Okay. And dr es obvio que es dx, dy, dc. Entonces, when you perform the dot product in between f dot product dr, bueno, es obvio que this is multiplication by this, and this is multiplication by this, and this is multiplication by this. But by coincidence, this function PQR is the same, and you factor out. If you factor out, you have x. No angular bracket anymore. X, this is a scalar now. I did the dot product, no? Multiplication by dx, dy, dc. So this is very, very weird, in my opinion. However, this is now a little bit clear. I illustrate this because, you know, so you see that, you say, no, I don't understand anything, professor. This is, what is that? What is the, this is no problem. No, this is just multiplication, the regular multiplication. Okay, so what is f and what is dr? I have no idea. I know this, you have idea. This is f, and this is dr. Clear or no confusing? I know it's confusing, eh? Gerardo says clear. Okay, now ready to start, because I understand the weird part. What should I do? Compute the curve. Compute the curve of this vector field in which PQR are the same function. Okay, no problema. I try. Compute the curve. Compute the curve of this vector field. I, J, K. The symbolic way partial derivative with respect to x, partial derivative with respect to y, partial derivative with respect to c. And the function PQR are x plus y plus c. Exactly the same. Let's do it. Remember, I par. You delimit all this and this. Okay, partial derivative that r with respect to y is 1. And partial derivative with respect to c, this is 1 also. There is subtraction because the determinant. This is 0i minus j. You delete now this and this. And you differentiate this and this is 1 again. Here, partial derivative, let me see. Partial derivative with respect to x of this expression is 1. And partial derivative, this expression with respect to c is 1. So 0j. Now, in the k part, is this and this, delete. Stay alive only this partial derivative with respect to x of this expression is 1. And partial derivative, this expression with respect to y is 1. Wow, again is 0, 0k. Now it is the 0 vector is 0, 0, 0. That means that our vector field also is conservative. Therefore, I need to find the potential function, but I will need to do more. After the potential function, you evaluate the potential function in this endpoint minus a start point in order to find the value of this line integral. Okay, let's do it. Potential function. Easy. Integral p dx. Integral q dy. Integral r dc. In this case, a coincidence que es the same. Sorry. Dx. Let me set out after I do that, because it's similar. Okay, let's do it. Integration with respect to x. It's obvious que es x squared over 2, the first part, no? But the second is xy, integration that part with respect to x, and this is xc. Well, something I don't care. This is xy, this is y squared over 2, and this is cy plus something. This is now xc, this is yz, and this is c squared over 2. Entonces now ready to set up or copy the potential function, que es a scalar function, que depending only of 3 variables. Entonces you organize in that way. You take, for example, you take this, the quadratic first. Okay, entonces es x squared over 2 plus y squared over 2 plus c squared over 2, no? And you take also the, for example, this, but this is repeated here. You take one time. xy, xc is repeated again. xc and yc is this and this. This is my potential function. cy, yc, whatever you want. Okay, this is my potential function. So now my line integral, the original line integral, this one, I want to copy again. Look, from the point 0, 0, 0 to the point 1, 1, 1. Of this weird way to express this case, parenthesis x plus y plus c, parenthesis dx plus dy plus dc. At the beginning we don't understand very well, but we translate to the vector field and we determine which peak you are and dr. Now it's equivalent to evaluate this function in 1, 1, 1, que es the end point, and the start point, que es 0, 0, 0. Es obvio que 0, 0, 0, when you plug it in here, is 0. So the answer of this is 0. And the answer of this is 1/2 plus 1/2 plus 1/2 plus 1 plus 1 plus 1, ¿no? Entonces the final answer is 9/2. Okay, this is the number that we get in the other example, 9/2. So it's 1/2 plus 1/2 plus 1/2 plus 1 plus 1 plus 1, ¿no? This is 3/2 plus 3, no? Boom. Any question? Any question? No? Basically, the thing that we are doing was the fundamental theorem of calculus applied for line integral. Okay, que the fundamental theorem of calculus applied for the line integral say you have one integral and you discover que the vector field, okay, it's a vector field that dr in one specific curve. Pero you discover que this vector field is the gradient of the one hypothetical potential function, no? Now dr. And you evaluate in the curve, well, suppose the curve is not closed, in this case not closed, you evaluate the potential function in the start point and end point. End point first and start point secondly. Exactly the same thing that we are doing in Cal 1. In Cal 1 we have antiderivative of the derivative. Okay, this is analogous. Look, first derivative is analogous in 3D gradient from A to B. You compare the antiderivative. An antiderivative is the original function, evaluating between B and A. You are super familiar with this idea, but this is more general because this maybe is in 2D or in 3D. Okay, you compute the gradient. No, you compute the gradient. No, you have the vector field. You determine if this vector field comes from the gradient for the one hypothetic function because it's conservative. Yes, it's conservative or no, not conservative. Well, si it's conservative, super. Now you evaluate. So not necessarily, I don't care. I don't care what happened. Look, 0, 0. This is the 3D, X, Y, and Z. Okay, my start point is 0, 0, 0. And my end point is 1, 1, 1. I don't care. Well, it's totally in path independent. See, it's like that, or like that, or like that. I don't care. I don't care. I don't care. Always, well, the direction is important. The direction is always from the beginning to the last point. Okay. Direction is important. See, it's opposite direction, it's opposite sign. So you feel strong, you feel good in that part. It's complicated, it's easy. Number 6 is very similar problem. Feel good. Okay. Number 6 is very similar. Okay, let's try to do. See, we have no time to finish. We continue next time. Number 6. Number 6 is look. Number 6 question. Number 6 question is one line integral again. When you see this guy, que specification the point is a clue, no? You are a smart guy. Okay, give me information. Okay, you apply the fundamental theorem of the line integral because I don't care the path. So no specification, see, no parametrization, the curve, only the original point and the last point, and no C, no parameterization. It's because it's path independent. Si it's path independent, it's because the vector field is conservative, but I have no idea what the vector field. Again, give me the line integral and the weir. No weir, but in this case, it's like a P dx, Q dy, and R dc, no? Something like that. This is the another way to express the frequently way is like F dot dr, no? So I need to determine who is F. Who is, well, I know who is dr. Dr is a vector, dx, dy, dc. But P is, I suppose que P is xyz. Let me see. Using my intuition, my common sense, my imagination, when you perform that dot product, look, your multiplication x times dx. A ver, no. I make a mistake, no? No. It's x. Okay. I need to change this. Look, I could be wrong in my paper, but I fix it now. Okay, so I suppose that the vector field is y here, because y multiplied by dx, no? Comma. Y dx. I mean, let me see if I copy wrong or copy right. Yeah, I copy right. Let me see in the original problem. Yes. Comma, who is the guy que multiply by dx? Es y. What is the guy que multiply by dy? Es x. And what is the guy que multiply by dc? Es c. Okay, this is my vector field. Let me fix it in my paper. I suppose that this doesn't change the meaning of the problem, but it's important to do good. Y, x, and z. Do you follow me? I am doing well, or I am making a mistake? Remember, I am a human guy. Okay, entonces normally I make a mistake. Entonces I make a mistake frequently when I underestimate the thing. Entonces, yeah, it's a piece okay for me. Entonces, I don't pay attention, 100%. Entonces I make a mistake. Okay, let me do again. Redo again. Okay, si I assume que this is my vector field, y, x, z, dot product, dx, dy, dc. When you perform the dot product, it's y dx plus x dy plus c dc. Is perfect coincidence with the integrand function or no? Yeah, The only thing is that I copy in different order, but it's okay. Okay? Entonces, what should I do now? See identification of vector field. I compute the curve. I compute the curve of this guy. Okay, let's do it. Curve of this is I, J, K, partial derivative with respect to x, partial derivative with respect to y, partial derivative with respect to z. Entonces now the ordering is y here, x here, and z here. Okay. I, J, K. Paréntesis, paréntesis, paréntesis. You delete mentally this bar. Partial derivative, 0 minus 0. Wow. Delete this bar and this bar. Partial derivative is 0. 0 minus 0. And K, this and this. Partial derivative y is 1. Partial derivative is 1. Es 0. Entonces, this curve is a 0 vector, que es 0, 0, 0. Therefore, it is conservative. Therefore, we need to find the vector function, but not today. We find the vector function Friday. We continue Friday. Okay, guys? It's important, everyone, don't be absent. Any lecture from today. This is a crucial moment in the course. Okay? If you be absent, you are in big